Let me know if I'm absolutely moving too fast through this section, but also keep in mind that you can pause the video. In fact, I'm anticipating you will need to pause the video and look at these examples and things as we're going through acids and bases. So there are several definitions of acids and bases, and this is the oldest one, that acids produce hydrogen ions in solution and bases produce hydroxide ions in solution. Now keep in mind that even though we don't often draw this, that really what's happening when we say we produce hydrogen ions in solution is the hydrogen ions are combining with water and making this hydronium ion. And so we often use this hydronium ion interchangeably with the symbol H+. So you may see either one of those or both of those, and they kind of mean the same thing, but the hydronium ion is probably the most accurate representation of what's going on. The second definition of acids and bases deal with the Bronsted-Lowry definition. And notice that the acid is the proton donor, and the hydrogen ion, remember, is just like a proton. And so the proton there you see is being donated to the base, in this case the base being water. So that we always have this system where we have a acid and a base. The acid is the proton donor, the base is the proton acceptor, and the particle that remains after the acid has lost its proton is called the conjugate base of that acid. So those are the terms you want to be familiar with, and a couple of examples here. You'll look at the examples in the assignment as well. So here is one example, and notice that these always occur in pairs, and you should be able to identify the acids, bases, and conjugate bases in any of these kinds of systems. Now often it becomes vitally important to be able to look at things like this species and identify it as the conjugate acid of some base, or to look at this and identify it as the conjugate base of some acid. Of course, you should study the properties of acids and bases, and maybe we'll just put the acids and bases song on as a totally separate video because it won't fit here. But be sure you look at these things, including things like taste and how pH indicators are affected. You should know those. Or the pH scale, at least in general terms, and actually we look at that a lot more specifically. So just like we've been working with dissociation constants, acids also dissociate, and we can put them into a acid dissociation equation, and that acid dissociation equation is going to look just like the equilibrium expression that we were looking at in the previous chapter. A large acid dissociation constant means that this reaction we're looking at up here goes mostly to the right. It mostly dissociates so that we have a lot of products and not very much of the original acid left over. The larger that Ka, the more completely the acid is dissociating. Another way of saying that is the acid is a stronger acid. So we can always look at a table of acid dissociation constants, Kas, and get an idea of the relative strength of those acids. And a larger Ka also means a weaker bond right here holding this together. And so if you compare these two acids, which one has the weaker bond holding the hydrogen to its conjugate base? Well, this bond would be weaker because it's a stronger acid. So this table is from your book, and it's kind of a survey of what you can tell about acid strength from things like the Ka and how that affects the conjugate base of those acids, and a lot of information, so study and be familiar with everything on this table. Be able to write acid dissociation reactions. Look at those examples. Study the examples on page 625. They're right there for you to study on page 625 of Zumdahl 6th edition. Oh, it's the 6th? No, let's see, 7th edition. In strong acids, the equilibrium lies far to the right. The system is mostly ionized. In weak acids, they're going to yield a weak conjugate base. That's this part right here. It is actually a base. Weak acids will yield strong conjugate bases. In strong acids, that conjugate base is weaker even than water, a weaker base than water. Study those examples. And these slides just kind of summarize some of those things. So keep in mind that sulfuric acid is kind of a special case in that this is a strong acid and it dissociates almost completely into hydronium ions and hydrogen sulfate ions. Now this hydrogen sulfate has a proton that can also be released, but it is a weak acid. And so we would have to draw a second equilibrium system for this. The first one would have a Ka1 that would be very large, and the second would have a Ka2 that would be considerably smaller. So in these cases, you're going to see the acidic hydrogen here in these particular carboxylic acid systems, a hydrogen that can easily be removed. That's what makes these weak acids. Here we see a table of weak acids from your textbook. You'll refer to this frequently as you're working on these kind of problems. Sorry, I was checking my clock to see how long I've been talking. Let's see. Anyhow, you'll refer to this. The basic thing you want to get is here, the smaller this number, the weaker the acid, but the stronger the conjugate base of that acid will be. So this conjugate base I've circled right here will be a stronger conjugate base than, say, this conjugate base right here. Because this acid, the hydrogen sulfate ion that we just looked at in the previous slide or two, that is a stronger acid because its Ka is larger. So its conjugate base, the SO4, sulfate ion, SO4 negative 2, will be a weaker conjugate base. So